All right, 3.4, polynomial functions. Graphs, applications, and models. And don't worry, I'm not making you like graph these by hand or anything. I'll be graphing them on a calculator, but then using that to do the rest of the stuff. All right, so where am I looking? All right, so the first thing is turning points. And this is, or I would say that a polynomial of degree n has at most n minus 1 turning points with at least one turning point between each pair of successive zeros. So if you had something like a like an x to the 4th graph, okay, it looks something kind of like that. It kind of looks like a W. So it comes down, it turns around, it comes up, turns around again, comes down and turns around. So there would be 4 zeros, okay, or the n value, I should say, would be 4. Okay, it turns around 3 times. 1, 2, 3. So n minus 1 is how many times it turns around. All right, this next thing is the big part of this section. It is in behavior. Of graphs of polynomial functions. So in behavior is what's happening as the graph is getting really, really far out. Where's it going? So suppose that a times x to the n is the dominating term of a polynomial function f of odd degree. So we're going to do odd first, and then we'll go to even in a second. So in terms of like it's raised to like the first, the third, the fifth, so on and so forth, power. Then we have if a is greater than 0, then x goes to infinity. Or let me say, then as x goes to infinity, f of x also goes to infinity. And as x goes to negative infinity, f of x goes to negative infinity. Therefore, the end behavior is of the type something like where a is greater than 0 when n is odd.
This is weird. Is it going to make more sense when we start doing examples?
Well, yes and no. I mean, yes, it's going to make more sense than this, but it's probably still going to be confusing.
Okay.
I always say, like, you're looking at what happens as x gets really, really big to the function. Is it going up or down? That's basically what's happening.
Okay.
Is it going to infinity or negative infinity? Now, that's a whole other story when it starts going to, like, 3 or 5 or negative 100. Like, that's a different thing. But this right now is just what's happening when it gets really, really big or really, really small,
Okay.
like in the negative direction. So then the other option is if a is less than 0, then as x approaches infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to positive infinity. Therefore, the end behavior is of the type, and so basically it's just a reverse of what we just drew. It's just a mirror image of it, basically. I can't even draw it backwards. Good enough. For a less than 0, n being odd. So both of those are the case where n is odd, so you have an odd power that it's being raised to. And again, that's the leading term, the highest powered term is what we care about. We don't care about all the stuff that follows it. And then suppose that a x to the n is the dominating term of a polynomial function of even degree. So now we're looking at like 2, 4, 6, 8, so on and so forth. So if a is greater than 0, then as the absolute value of x, because remember it's even, meaning whatever happens is becoming positive. There's no way for something being raised to an even power to be negative. So as the absolute value of x approaches infinity, f of x approaches infinity. Therefore, the end behavior is of the type, so these are gonna, just the basic is gonna look like a parabola, basically, for a greater than 0 and n being even. And then if a is less than 0, then as the absolute value of x goes to infinity, f of x goes to negative infinity. Therefore, the end behavior is of the type so it's just flipped upside down. So a is less than 0 and n is even. It would look like that. So even functions are always going to end like with the whole thing facing up or the whole thing facing down, whereas odd functions are going to have like a weird curve to them, and so one part's going to be going down and one part's going to be going up. So with even, both arrows at the end of your graph are facing the same direction. Odd, they're going to be facing opposite directions. And if you need to like think about it, think of it as like the most basic, like if you graph a line, you've got one arrow going this way. Now we don't typically draw the arrows on them anymore, but when you first learned graphing, I'm sure whoever taught you graphing was like, make sure you put the arrows on it, make sure you show that it keeps going. Like that's why, because it keeps going. So you have, with a line, it's going in opposite directions, but with a parabola, like it's both going up. So that'll kind of help you too. As far as graphing, like I said, we're not going to actually graph them yourself. Your calculator's going to do that for you, because when you get out in the real world, as Kenny would say, you always get a calculator. So, well, that's a fair assessment. His boss one time not yelled at him, but made fun of him because he was doing all these like super, super hard calculations by hand. And his boss was like, you have a calculator, dude, just use it. And he was like, yeah, but I don't know, it's just... He was like, dude, save yourself the work. Just do it on a calculator. Like, so you have a calculator, take advantage of it. All right, this next thing, we kind of talked about it when we did the synthetic division before break, but the relationship among x-intercepts, zeros, solutions, and factors. If f is a polynomial function and you have the point C0 is an intercept, specifically an x-intercept of the graph of y equals f of x, then C is a zero of f, C is a solution of f of x equals 0, and x minus c is a factor of f of x. So we kind of saw that when we were doing the synthetic, because we were trying to figure out if things were factors. We were writing the linear factorization. So once you found like that it was a 0, you had to then change it into a factor. Anyway, so that's just kind of actually seeing that written out, that's what that is. All right, next thing is the intermediate value theorem. Which we use a decent amount in calculus. So if f of x is a polynomial function with only real coefficients and if for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real 0 Because remember, we can have imaginary zeros and complex zeros and all that. At least one real zero between A and B. Now, this helps to identify that there is one. In terms of actually finding what it is, we have to if f of A and f of B are opposite in sign, then 0 is between f of A and f of B. So there must be a number C between A and B where f of C is equal to 0, which would be what the 0 is. And the book warns to be careful when interpreting the intermediate value theorem. If f of A and f of B are not of opposite sign, it doesn't necessarily mean that there's not a 0 between A and B. But it's saying that if they are opposite, there definitely is one. So there could be one, but there doesn't have to be if they're the same sign. All right, and then the last notes thing is the boundedness theorem.
Are we starting examples today too?
Possibly. Probably do some, but probably not all of them. So the boundedness theorem says let f of x be a polynomial function of degree n greater than or equal to 1 with real coefficients and with a positive leading coefficient suppose f of x is divided synthetically by x minus c if c is greater than 0 and all numbers in the bottom row of the synthetic division are non-negative, then f of x has no 0 greater than c, then if C is less than 0, and the numbers in the bottom row of the synthetic division alternate in sign. So positive, negative, positive, vice versa. And we'll consider 0 as positive or negative as needed. Then f of x has no 0, less than c.